about integrating rational functions, rational expressions. So we'll spend a lot of time with partial fraction decomposition, which is where you take a combined rational expression and divide it into parts, and then you have a bunch of little pieces that are easy to integrate. But first we have to make sure that we have a proper rational expression, meaning that the degree of the numerator needs to be smaller than the degree of the denominator. Otherwise it's improper. Just like an improper fraction with numbers. If you can divide the bottom into the top, it's an improper fraction. For example, example 1. The degree of the numerator is 3. The degree of the denominator is 1. Now, since it is 1 and it's a nice, simple linear expression, we can use synthetic division. You don't have to, but if you happen to remember it, you know synthetic division is really easy. So our coefficients in the numerator are 1, the squared term 0, the first degree is 1, the constant is 0. 1 falls down, and remember it's always the opposite of whatever is here because it's x minus a. And the a goes there. So 1 falls down, 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, 1 plus 1 is 2. And you're done. Well, you need your remainder, so 1 times 2 is 2, so 2. So that means that x cubed plus x over x minus 1 is equal to, this is your squared, plus x plus 2 plus 2 over x minus 1. So this integral is the same as the integral of x squared plus x plus 2 plus 2 over x minus 1. Well, that's super easy. Add 1 to the exponent, divide by the new exponent. Add, divide. Give it an x, and now u is equal to x minus 1, du is equal to dx, so this is 2 times the natural log of the absolute value of x minus 1, not plus 1. Plus a constant. Easy enough. So nothing fancy there. Just be sure you do your division first. And again, you don't have to do synthetic division. You could do long division. And we'll do some of those in a moment. There's example 1. And there's my pretty answer. Okay, so integration by partial fractions. Your first step is to do your division. After that, you want to factor the denominator as much as you possibly can. So, you want to factor it until you have linear factors and irreducible quadratic factors. Case number 1 is the friendliest. That's when we have a product of distinct linear factors. Then you can rewrite it as some number, and I call them your alphabet letters, living on top of each of your linear factors, and we add it together. So this is kind of a long example. Your homework will start with something a little simpler than this. Here's example 2. We have the integral of x squared, and notice that the degree of the numerator is less than the degree of the denominator, so I don't have to do any factoring. Any dividing, excuse me. I am going to factor, and I'm going to go ahead and factor an x out of this denominator and get 2x squared plus 3x minus 2. And since this example is supposed to have linear factors, I know good and well this thing factors. So just because you know by now that I'm kind of lazy about rewriting things, I'm going to factor right here below And I'm going to use the guess and check method because there's not that many ways to multiply and get 2x squared. There's 2x times x. There's not that many ways to get negative 2. There's 1 times 2, and one of them has to be negative. We want a plus 3 in the middle. So that makes me think I want 2 times 2 gives me 4x minus 1. Because then I'll have minus x plus 4x gives me plus 3x in the middle. Minus 1 times 2 gives me minus 2. So that means I could rewrite x squared plus 2x minus 1 over x times 2x minus 1. Now, the degree of my original denominator was 3. That means I need to have 3 terms when I decompose. The first one is just going to be a over x, b over 2x minus 1, and c over x plus 2. So we're just undoing that least common denominator that you would get if you started here and ended up at our original problem that we had. So now I'm going to multiply both sides by the least common denominator. When I multiply this side by x times 2x minus 1 times x plus 2, the whole thing just cancels. So I'm left with x squared plus 2x minus 1. Now when I multiply this side by x times 2x minus 1 times x plus 2, I distribute that through. Here the x cancels, so I have a times 2x minus 1 times x plus 2. I'm getting rid of the fraction. This one, the 2x minus 1 cancels, so I have bx times x plus 2. Here the x plus 2 cancels, so I have cx times 2x minus 1. Now I'm going to make some life choices, and I'm going to make good life choices. I am going to make the choices that allow me to figure out what a, b, and c are very easily. I can let x be anything I want to. So first thing I do is I figure out what makes a's denominator equal 0. Well, if x is equal to 0, then negative 1 is equal to a times 0 minus 1 times 0 plus 2. The x is equal to 0, so b disappears and c disappears. So negative 1 is negative 2a, so a is a half. Now I'm going to see what happens when b's denominator is equal to 0. So if 2x minus 1 equals 0, x has to be equal to 1/2. So 1/2 squared is 1/4 plus 1 minus 1. A times 0, c times 0. I just have b times 1/2 times 1/2 plus 2 would be 5/2. So 1/4 is equal to 5/4 times b. Multiply both sides by 4 over 5. So b is a 1/5. Let c's denominator be equal to 0. So x plus 2 equals 0, means that x equals negative 2, which means that a times negative 2 plus 2 is 0, disappears. b times negative 2 plus 2 is 0, disappears. So I just have negative 2 squared is 4, minus 4 minus 1 is equal to c times negative 2. And negative 2 times 2 is negative 4, minus 1 is negative 5. So it looks like I have 4 minus 1 is equal to 10c. So c is equal to negative 1/10. So I'm going to take a minute and I'm going to replace my alphabet letters with the numbers that I got. And I'll do it on another sheet of paper. So I have the integral of a was 1/2 over x, b was 1/5 over 2x minus 1, and c was negative 1/10 over x plus 2. So, easy. 1/2 natural log absolute value of x. Now this one, u would be equal to 2x minus 1. du would be equal to 2 dx. So we would end up with 1/2 times the natural log. So I'll have 1/5 times 1/2 times the natural log of the absolute value of 2x minus 1. And then the last one here, minus 1/10. u is x plus 2, so du is dx. So natural log of x plus 2. And don't forget to add c even if you write too big and run out of room. And there's the pretty answer. Here's a simpler one. Practice number 1. So take a minute, see if you can do it on your own, and then we'll come back and compare answers. So how did it go? First thing we did was, it was pre-factored. We didn't even have to factor. We just rewrote it as decomposed, a sum of 2 terms. And when there's only 2 terms, it's really super easy. You just have a times b's denominator and b times a's denominator. Let a's denominator equal 0 to figure out what a is, and let b's denominator equal 0 to figure out what b is. I ended up with b is 1 over 9 and a is 4 over 9. And similar to the last one, this one was easy because dy was equal to du when you let u be equal to y plus 4. Here, if you let u be equal to 2y minus 1, then du is 2 dy, so you have to multiply by 1/2. Easy enough. Let's look at a definite integral and notice that the degree of the numerator is not smaller than the degree of the denominator, so you need to long divide first or you're going to lose a term. Long divide. How'd that long division go? First thing we did was divide x squared plus 3x plus 2 into your numerator. So you do that before you factor. It just goes in there 3 times. So the big thing was figuring out what the remainder was. So the remainder goes on top of the original denominator. Then we factor the denominator. Don't forget my parentheses. Then I did my partial fraction decomposition. It was a pretty simple one. We just crisscross applesauced. And then we let the numerators be equal to 0. So I figured out what b was. I figured out what a was. They were super easy to find, the integrals. And you could even simplify this a little bit more because you could use the laws of logarithms, but I'm not interested in doing that. But on test day, you will need an exact answer, so you can't just plug it in your calculator and get a decimal approximation. Next one is where we have a product of linear factors, and some of them are repeated. So you're still going to need to have as many factors as the degree of your denominator. It's kind of like when you're finding the least common denominator with numbers, and if it has 4 as one of the factors, it could have 2 or 4 as one of the original fractions that you are finding the common denominator for. So let's look at an example. You have to have a term for each repeated factor as many as it is repeated. So if it's repeated twice, you have a plane and then you have a squared. If it's repeated 3 times, you have a first degree, second degree, third degree. Example, real life numbers, it'll make sense. Example 4. First thing I do is I realize I'm going to have to do some long division on this one. But let's talk about the denominator first. We have x cubed minus x squared minus x plus 1. I want to factor that thing. Well, it has 4 terms, so my only hope is to factor by grouping. Let's see if that'll work. I have x cubed and x squared. I could factor an x squared out, and I'm left with x minus 1. I have minus x plus 1. I could factor a minus 1 out, and I'm left with x minus 1. Now I have a common factor of x minus 1 times x squared minus 1. That's a difference of 2 squares. I have x minus 1 times x minus 1 times x plus 1, which is x minus 1 squared, times x plus 1. Now maybe you're having a bad day, you're kind of nervous because it's test day. Then you would just pull out your calculator and you would go to PolySolve. It's a third degree polynomial. So we would have 1, negative 1, clear that out, negative 1, clear that out, and 1. And we have x1 is minus 1, positive 1, positive 1. So we know that it's x minus 1 times x minus 1 times x plus 1. Because it's always x minus whatever your zeros are there. But first, let's go through and do our long division, because we do that before we do the decomposing. So we have x cubed minus x squared minus x plus 1 goes into x to the 4th. Oh, there's no cubed term, so I'm going to put a 0 x cubed there as a placeholder because I don't want to get lost in my division. Minus 2x squared plus 4x plus 1. So what do I need to multiply x cubed by to get x to the 4th to come out? I would say that would be x. So x cubed minus x to the 4th minus x cubed. X times x is minus x squared, and x times 1 is plus x. But I'm going to subtract all of that from the row above it. That will disappear. That becomes a plus. That becomes a plus. And that becomes a minus. I always label them so I don't get lost. So 0 plus 1 is x cubed. Minus 2 plus 1 is minus x squared. And 4x minus x is plus 3x plus 1. And now, what do I need to multiply x cubed by to get x cubed? 1. X cubed minus x squared minus x plus 1. That goes away just like we wanted it to. That becomes a plus, that becomes a plus, that becomes a minus. So minus x squared plus x squared, hey, bonus, that goes away. 3x plus x gives me 4x, and 1 minus 1 goes away. So I ended up with a remainder of just 4x. So my integral, I'm not going to copy down the original. I'm going to write down the x plus 1 plus 4x living on top of, and I'm going to go ahead and factor it because my hand gets tired of writing. Now I'll do my partial fraction decomposition. So 4x over x minus 1 squared times x plus 1 has to be equal to a over just x minus 1 plus b over x minus 1 squared plus c over x plus 1. Okay, so we have to have a plain old x minus 1, and then we have to have an x minus 1 squared, because you have to count up to that exponent on your repeated factor. So 4x is equal to, now when I multiply both sides by the common denominator, one of the x minus 1's will cancel. I'll be left with a times x minus 1 times x plus 1. X minus 1 squared will cancel here, so I'll have b times x plus 1, and x minus 1 plus 1 will cancel here, and I'll be left with c times x minus 1 squared. So I'll be able to make good life choices to figure out b and c, and then we'll have to go back and figure out what a is. So that makes these a little more complicated. So let's let x be equal to 1. Then 4 is equal to, that one disappears, that one disappears. I'm left with b times 1 plus 1 is 2. So b is equal to 4 divided by 2. I let x be equal to minus 1. I can figure out what c is. Then minus 4 is equal to, a disappears, b disappears, c, I have minus 1 is minus 2 squared, which means minus 4 is 4c, so c is minus 1. At this point, I go back to this equation here, not the one with the fractions, but the next one, and rewrite it as 4x equals a times x minus 1 times x plus 1. B was 2, so 2 times x plus 1. And c is minus 1, so let's go ahead and say that's minus x minus 1 squared. And now you can let x be equal to anything you want except 1 or minus 1. My favorite, let x be equal to 0, because 0 is fun and easy. So 0 is equal to a times 0 minus 1 times 0 plus 1, 2 times 0 plus 1, minus 0 minus 1 squared. So I have 0 is equal to minus a plus 2 minus 1 squared is 1, so minus 1. So if I add a to both sides, that means that a is equal to 2 minus 1, which is 1. That was a lot of work to get a 1. So I'm going to take a minute and write my new integral on the next page. Now, when we have repeated linear factors, it's not just going to be a bunch of natural logs. This one's going to give me a natural log. That one's going to give me a natural log. But this one, I would let u be equal to x minus 1. du is dx. But I have the integral of u to the minus 2 power, so I'll be adding 1 to the exponent and dividing by the new exponent for that one. So this is equal to add 1 to the exponent, divide by the new exponent. Natural log, absolute value of x minus 1. Add 1 to the exponent, divide by the new exponent, so x minus 1 to the minus 1 over minus 1, and then minus the natural log of the absolute value of x plus 1. Never ever forget to add c. And yes, you could write that prettier as x squared over 2 plus x natural log absolute value x minus 1 minus 2 over x minus 1. But I would certainly give you full credit for the first answer. And here's your pretty solution. And oh yeah, I used some laws of logarithms here. I could combine this as natural log of x minus 1 over x plus 1, because this one has a minus sign in front of it, and you know that natural log of a minus natural log of b is equal to the natural log of a over b. But again, that first answer there is fine with me. Okay, practice number 3, it's pre-factored for you. The degree of the numerator is 2. The degree of the denominator is 3, so you don't have to long divide. Give it a try, and we'll compare our answers. Okay, this one took some algebra. So first thing I did was I gave it its alphabet letters. I put a over 3x minus 1, b over x minus 1, and c over x minus 1 squared. I made my good life choices so I could figure out what a and c were. I plugged a and c back into this equation with the alphabet letters. That left me with only b as my unknown, and then I let x be equal to 0 because it makes my life easy, and I figured out that b was minus 2. So then I had something that's going to be a natural log, and a power rule. Easy peasy. I did my integrating. I evaluated from 2 to 3. And again, you could use laws of logarithms to simplify this if you wanted to. Remember, this is the same thing as the natural log of 8 to the 1/3 power, which would be the natural log of 2. This is 2 squared, which is natural log of 4, and minus natural log of 5 to the 1/3 power. So you could combine that all into one natural log if you really wanted to, because you have a difference of natural logs there. I'm fine with an exact answer that looks like that one. You don't have to show off your knowledge of laws of logarithms unless you just want to. The final and most complicated case is when we have irreducible quadratic factors. Actually, it's not the most complicated because they could be repeated. That would be even worse. So, irreducible quadratic factors, none of which is repeated. That's the next case. So, sometimes they're not too bad. If it's something like x squared plus 1 or x squared plus 4, remember the antiderivative of 1 over x squared plus a squared is 1 over a times inverse tangent of x over a plus a constant. And you can get that by rewriting this as 1 over a over x over a squared plus 1, and doing u substitution with u is equal to x over a. Or you can just have it memorized. I don't care. You can memorize that one. It's pretty easy. You're going to need that when you have irreducible quadratics. So let's look at an example. Example 5. I'm going to go ahead and factor that denominator because I can. I check to be sure that it's a proper rational expression, and it is because the degree of the numerator is 2. The degree of the denominator is 3. So it's x times x squared plus 4. So I'm going to partial fraction decompose this over x times x squared plus 4. The linear part works just like it did, a over x. But for your irreducible quadratic, you have to put a linear on top of it. So it's bx plus c over x squared plus 4. So, again, you're going to have to work a little harder. It's not going to just have the answers pop right out at you like it does when you have just plain old non-repeating linear factors. 2x squared minus x plus 4. First part's easy, just rewriting it as a times x squared plus 4. And bx plus c times x. Then I let x be equal to 0. I can figure out what a is. Times 0 plus 4, and b and c disappear. So a is equal to 1. Alrighty, so now I go back and I do 2x squared minus x plus 4 is equal to 1 times x squared plus 4. And I'm going to distribute this x. I have bx squared plus cx. Now I'm going to get all my stuff with no alphabet letters on the left-hand side of the equal mark. So I have 2x squared minus x squared gives me x squared. Minus x goes away, and 4 minus x stays the same. There's nothing to combine with it. And 4 minus 4 disappears. That's equal to bx squared plus cx. The coefficient of x squared has to be equal to b. And the coefficient of minus x, coefficient of x, has to be equal to c. So usually that's how it's going to work out for you. So now we'll rewrite this integral, and it was a over x, and a was 1. 1 over x, x minus 1, so bx plus c over x squared plus 4. Now we're going to have to divide that irreducible quadratic part into 2, and it's always going to work this way. You'll always have one natural log piece and one inverse tangent piece. So we have the integral of 1 over x, x over x squared plus 4 minus 1 over x squared plus 4. Here, u is equal to x squared plus 4, du is equal to 2x dx. So when we integrate here, we'll have half of the natural log of u, which is the denominator. First one's easy. half of the natural log. You can give it its absolute values if you want, but you don't have to, because x squared plus 4 will always be positive. And then minus, this is x squared plus 2 squared, so 1/2 inverse tan x over 2 plus a constant. Example 6. At first glance, we think, is this an irreducible quadratic? Well, let's find out. I'll plug it into my calculator. So let's, second PolySolve. Actually, I need to quit. Now go back into PolySolve. Quadratic, we have 4. Clear out the old thing, minus 4. Clear out the old thing, oops, 3. And if you arrow over, you see that ends in an I. That is an imaginary number, so it is indeed an irreducible quadratic because it only has complex solutions. So this is an irreducible quadratic. We're going to have to work a little harder for this one because it doesn't just jump right out and say, hey, look at me, I am a inverse trig or an arctan, or hey, look at me, I'm a natural log. But before I do anything, I have to get it into proper form because the degree of the numerator is the same as the degree of the denominator, so I can do bottom goes into top. Luckily, they had the same leading coefficient, so I'll just have a 1 there. 4x squared minus 4x plus 3. Going to subtract the whole thing. That first term disappears. That becomes a plus. That becomes a minus. So minus 3 plus 4 is x. And 2 minus 3 is minus 1. So this is the integral of 1 x minus 1 living on top of this irreducible quadratic. There's no partial fraction decomposing to do in this one. This one's a little different. We're going to have to complete the square so we can make this into something we can divide into 2 pieces and have a natural log piece and an arctan piece. So let's review completing the square. First thing I'm going to do is write it down, and I'm going to factor 4 out of the first 2 terms here. So x squared minus x. I need to leave a blank spot. Plus 3. I take that middle term, middle coefficient, half it, and square it. So I'm going to add 1/4 on the inside and subtract 1/4 on the outside. So this is 4 times x minus 1/2 squared plus, and let's write this. I was copying it to the other side and luckily found my mistake. Remember, what I did was add 4 times 1/4 and for here inside the parentheses, so I really needed to subtract 4 times 1/4. So that's way easier. I don't have that silly fraction there. So it's really just 3 minus 4 times 1/4 is 1. So that would be 2. So this is times 2. Now, I look at this and I have 4 times x minus 1/2 squared. Well, this is the same thing as 2 squared times x minus 1/2 squared, which is the same thing as 2 times x minus 1/2 squared. which is the same thing as 2x minus 1 squared. Oh, that looks a whole lot better. No more fractions. So let's rewrite this as 1. Get my notation correct on that one before I rewrite it as x minus 1 over 2x minus 1 squared plus 2 dx. And now I'm ready to do some u substitution. Let u be equal to 2x minus 1. Du is equal to 2 dx. So du over 2 is equal to dx. So I have the integral of 1. I'm going to go ahead and divide it into 2 pieces. Then I'll have 1/2. I'm going to divide it into 3 pieces. X over, actually, let's don't. Now I'm going to have to work a little harder for this one. So I'm going to go ahead and rewrite x as a function of u's in terms of u so that I can do my u substituting. I'm going to separate it. I'm going to pull out just the 1 dx. And then I'm going to replace this x with u. Let's write it as 1/2 times u plus 1. Still have that minus 1 sitting there. And then I just have u squared plus 2 du. And du is sitting on top of 2. So I have, go ahead and do the easy one, the integral of just x. I have 1/2 and 1/2 here. So let's divide this into pieces. I have the integral of 1/2 of u plus 1/2 minus 1. All of that, and I'm going to pull the 1/2 out front, u squared plus 2 du. So all I did was distribute that 1/2 through the parentheses and then pull that 1/2 out front. 1/2. Now I'm going to divide it into pieces. I have 1/2 of u over u squared plus 2. And then I have 1/2 minus 1, so that's minus 1/2 over u squared plus 2. And don't lose your du's like I just did. One half times 1/2 is 1/4. This is my natural log part. So since I've already used u, I'm going to use v for this. V equals u squared plus 2. dv equals 2u du. So I have 1/2 of the natural log of u plus 2. I have minus 1/4 of the not natural log. This is your inverse trig part. So this is 1 over, this is u squared plus the square root of 2 squared. So it's going to be 1 over 4, 1 over square root of 2 times the inverse tangent of u over square root of 2 plus a constant. And now we're going to need to bring our u back, which was 2x minus 1. It's 1/8 natural log of 2x minus 1 plus 2 minus 1 over 4 times the square root of 2 times the inverse tangent of 2x minus 1 over the square root of 2 plus a constant. I'd much rather partial fraction decompose. Let's check and see if I did it right. X plus 1, and this is natural log of, oh yeah, that should be squared. Squared. So yeah, I did it right. I just made a little boo-boo writing it down. Okay. Practice number 4 is not that complicated, I promise you. You can tell because it's more like example 5. So give it a try. Don't be intimidated. You can do it. So first thing I did was make sure I didn't need a long divide, which luckily I didn't. Then I went ahead and factored the x out. Put my alphabet letters in. A over the x and bx plus c over the irreducible quadratic. I figured out what a was by letting x be equal to 0. I plugged in the 2 that I got for a, and then I got everything that didn't have an alphabet letter on the left-hand side. I equated my coefficients, so the coefficient of x squared had to be b, the coefficient of x had to be c, so they both happened to be minus 1. I divided it into 2 integrals. Here's my natural log integral. U is equal to x squared plus 3, so du is 2x dx. So I end up with half of the natural log of x squared plus 3. Don't need the absolute values because that's always going to be positive. And remember that square root of 3 squared is equal to 3. So this is x squared plus square root of 3 squared, so we get our arctan piece. And now finally, that most complicated example where we have a repeated linear factor. So I'm going to take a minute and get it written down for us. So it works exactly the same with repeated linear factors. If you have a repeated irreducible quadratic, you have to count up to the exponent. So I had to have a first power term and a second power term. And since they're irreducible quadratics, they have to have the bx plus c or dx plus e living on top. So they have to have a linear factor living on top. So then I do the same thing, multiply by the common denominator. I end up with a times x squared plus 1 squared because the x cancels. Bx plus c, one of the x squared plus 1's cancel, so I have x times x squared plus 1, and then plus dx plus e. And actually, I probably did have room for it because the x squared plus 1 squared is going to cancel. I'll just be multiplying by x. So I'll do the easy peasy part. Let x be equal to 0. Then I have 1 is equal to a times 1 squared. A is equal to 1, and that's all I can get. So I'm really going to have to work to figure out what B, C, D, and E are equal to. So let's put my 1 in for A into this non-fraction here. So 1 minus x squared minus 2x squared minus x cubed equals x squared plus 1 squared. So that would be 1 times x to the 4th power plus 2x squared plus 1. Now, I need to multiply bx plus c times x times x squared plus 1. So I'm going to go ahead and do bx squared plus cx times x squared plus 1. Yeah, I'll go ahead and do that. So I have b times x squared, so that's bx to the 4th power. Inners gives me plus cx cubed. Outers gives me plus bx squared. And last gives me plus cx. So that takes care of this piece. And then all I have to do is distribute x through that, dx squared plus ex. Whew, this is pretty ugly. So now I'm going to get all the stuff that doesn't have alphabet letters on the left. So 1's still here. Oh, no, it's not. I have plus 1, so I subtract 1 from each side. So the 1 disappears. I have nothing to combine with the x, so it's minus x. I have 2x squared and 2x squared. That disappears. I have minus x cubed. And then I have minus x to the 4th power. Now let's put our alphabet letters over here. We have bx to the 4th plus cx cubed plus b plus d times x squared and c plus e times x. Do the easy ones first. Coefficient of b has to be the coefficient of x to the 4th power. So b equals minus 1. C has to be the coefficient of x cubed. So c equals minus 1. Now I need to figure out what d is, but b plus d is the coefficient of x squared, and the coefficient of x squared is 0. So b, which is minus 1, plus d has to be equal to 0. D has to be equal to 1. C plus e, so minus 1 plus e, has to be the coefficient of x, and the coefficient of x is minus 1. So e has to be equal to 0. And now I'll write down my integral with its alphabet letters. A was 1, so I have 1 over x. B is minus 1 x plus c, so minus x minus 1 over x squared plus 1 plus dx plus e. D is 1, so just x plus 0 over x squared plus 1 squared dx. And now we have stuff that we can integrate. 1 over x minus x over x squared plus 1. So I have a natural log. I have a natural log minus 1 over x squared plus 1. I have an inverse tan piece, and then plus x over x squared plus 1 squared. I'll let u be equal to x squared plus 1. Magic will happen. The dx, du is 2x dx, and the x's will cancel, and I'll be very happy. So I'm going to just do my little cheat sheet here. 2x plus 1 du equals 2x dx. That one's an arctan. Again, u equals x squared plus 1, so du is 2x dx. And I think we can just write down our answers. I have natural log, absolute value of x. I need a 1/2 on this one, so minus 1/2. natural log of x squared plus 1 minus the inverse tangent of x, because it just had a 1, so life is good. And then I have to have 1/2 x squared plus 1, add 1 to the exponent, divide by the new exponent, so to the minus 1 over minus 1, plus a constant. And you could write that a little prettier, of course, but I'm just happy to have gotten through it. So let's make sure I don't have any mistakes here. Let's see, I have 1/2, I have arctan, I have 1/2. And you notice I didn't even give you a practice on those because they are very complicated and very algebra heavy. There was a lot of algebra in that one and not so much calculus. So work on those. You can do it. You got your WebAssigns to work on. You should be able to do your entire lab now, so get to work on that.